All right, so we're going to take a look here now at the next question on the next page. How might we be able to obtain a way to approximate values of f of x, like we were kind of doing up above, but ones that are even further away from 0? Again, our line approximation was pretty good, and it lasted for a pretty long time, but the quadratic approximation was even better. So how could I maybe make this approximation even better than before? Well, you might be able to think that, hey, if I used a quadratic to improve upon a linear function, maybe I could improve upon a quadratic by going up to my picture here and like, maybe I could make a function that's like cubic. Could you imagine something like this green function in there? And that models the blue function even better for even longer. But then I might ask the question, how could you improve upon a cubic function to make it even better? And you might say, well, wait a minute, Kyle, couldn't I maybe go to the 4th power? Maybe I could go do a polynomial raised to power 4, a quartic. And then you can say, well, could I get even better than that? And you go, sure. I mean, maybe you could go to a quintic polynomial, go to something to the power of 5. And then maybe I could go to the power of 6, and then the power of 7, and then the power of 8, and the power of 9. And I could just keep going. And so the question would be, well, maybe we could construct polynomials of higher and higher degree. That seems like would be a perfectly reasonable way to maybe try to work with something like this. So the difficult part, though, is if I wanted to go ahead and construct polynomials of higher and higher and higher degree, what would a formula look like for one of those polynomials? This is our new problem then, our new question here, which is, what would a formula look like for a local approximation if I didn't want to do a line, if I didn't just want to stop at a quadratic, and I guess I don't even necessarily want to stop at a cubic. I want to kind of like make a flexible formula template that would allow me to pick the degree of the polynomial that I want. Maybe I can make it highest power n and immediately know what it looks like. So let's go ahead and start here by saying, like, how about we imagine that our p of x is going to look like this? It's going to start again with a constant, c0. It's going to go c1 x to the first, c2 x squared, maybe c3 x to the third. And I can just imagine it's going to keep going and going and going. That power is going to keep getting bigger and bigger and bigger until I get all the way up to an x to the n. And there's probably a constant in front of that one too. What subscript would I give it? I should give it an n. Okay, so if this is the polynomial that I'm working with, I can try to go ahead and think about some new green properties, like we talked about a couple videos back, about what I would want to be true about this polynomial. So I'll say, like before, to ensure that p of x, quote, bends in the same way as f of x, we would need the following green facts. So here would be my first fact. I'm just going to write them out one at a time. I would need, again, f0 to be equal to p of 0, just like we did before. I'm going to need f prime of 0 to be equal to p prime of 0. But I'm also going to need f double prime of 0 to be equal to p double prime of 0. But I'm going to have to just kind of keep going and going and going with this. I'm going to need the third derivatives to match, and the fourth, and the fifth, and the sixth, and the seventh, and the eighth, all the way until I get to the nth derivative. Now keep in mind that this notation that I'm using here, we mentioned it earlier this semester. When I have this little n up here in a set of parentheses, that just means that I'm dealing with an nth derivative. Okay, so we're just saying we need all these derivatives to match. So I'm going to try to go ahead and figure out again, well then what are the c's? How do I find a formula for these different c values so I would know how to just like immediately write out what the polynomial should look like? right? Whatever the degree is. Well, again, we'll go ahead and start looking at the formula for p of x. And its derivatives. So we can see what we would need to be true to make all of these statements true. So I'll start here with what p of x is again. So again, remember it's c0 plus c1 times x plus c2 times x squared plus c3 times x cubed. And it just keeps going and going and going until I get to cn x to the n. And what I want to be the case is that when I plug in p of 0, or when I plug 0 in here for all the x's, I want that to be the same as f of 0. Of course, if you take a look at that polynomial, what do you get when you plug 0 in for all the x's? Well, yeah, you definitely just get back c0. And if I want that to be f of 0, then boom, I found a formula. Now, the cool thing is you might recall, if you look back on a previous example, if you look back on example number 2, or right what we did before example 2, you'll notice that this is the exact same formula that we used when we did the quadratic approximation. Okay, so that's super nice. Well, let's take a look then at the derivative of p of x. All right, so let's see. I'm just going to go one term at a time. This is just a bunch of sum rules and power rules. So let's see. Derivative of c0. Well, that's just 0. Derivative of c1 times x, that's c1. Derivative of c2 times x squared, that's 2c2 times x. Then I'm going to get 3c3 x squared. And I'm going to go on and on and on until I get to, the last one's kind of weird, ncn times x to the power, what would the new power on x be? It would have to be n minus 1. All right, power's got to go down by 1. Okay, no big deal. I know what I want to have happen here. When I plug in 0 for all the x's, I want to get the same answer as when I plug in 0 to the original function that I'm trying to model. So let's see. If I plug 0 in for all the x's, can you tell what you get back? Yeah, it's just going to be c1 again. And if I want that to be f prime of 0, then boom, I found a formula. Okay, I just need to do this for all of the rest of the c's. And notice we only have like a mystery number of them. So we're only going to have to do this a mystery number more times. Okay, well, don't worry. Let's stick with it. What's the derivative of c1? 0, yes. Derivative of 2c2 times x should just be 2c2. Notice over here, I'm going to get 6c3 times x to the first. Then on and on and on. Over here, things are going to start to get clunky. I'm going to kind of get a n, and then that n minus 1 is going to come down. And then I'm going to have c sub n and x to the, what's the new power on x? Yeah, it's going to be n minus 2. Okay, and again, I know that I need this second derivative. When I plug in 0 for all the x's, I want it to eventually equal f double prime of 0. So what do you get here if you plug in 0 for all the x's? Yeah, you get 2c2. And again, if I want that to be equal to f double prime of 0, I can go ahead and re-express that as a formula where c2 is equal to f double prime over 2. Okay, so this is great. We're building these formulas. We found what C0, C1, and C2 are. I need to keep going. All right, so let's see. Let's go to a third derivative. All right, so P triple prime. Just gotta keep this going. What's the derivative here of 2C2? Yeah, that would just be 0. The next one is 6C3. And then I'm going to have dot, dot, dot. And, oh gosh, this is annoying. I'm going to get n minus 1. This big n minus 2 is going to come down. I still have the c sub n. And I'm going to have x to the n minus 3. Okay, what happens when I go to this third derivative and I plug in 0 for all the x's? Yeah, the only thing I'm going to get left back here is 6c3. And I know I want that to be equal to the triple derivative of f with 0 plugged in. So again, if I turn that into a formula for C3, that's the third derivative with 0 plugged in, divide by 6, and boom, I have a formula. Okay, how many more times do we have to do this? Well, The answer should be, I don't really know, right? I mean, it kind of depends on when someone tells me to stop. If I want to create a third degree polynomial, well, I'm done. I only have to go to C3. But we were going to try to construct here a polynomial of degree n. So we're going to go ahead and say, why don't we skip ahead to the nth derivative? Well, let's think about this. Notice that by the time we took the first derivative, x to the first power was reduced all the way down to a constant. When we took the second derivative, that x squared had completely disappeared by that point. When we took our third derivative, that x to the third was completely removed and only what was left in front of it remained. So by the time I take my nth derivative, that c sub n and the x to the n term, that'll be the only thing that remains, but the x will have completely vanished and I'll only have the constant. Can you start to tell, though, what that constant is going to look like? Because notice here, I'm going to have like an n minus 1, n minus 2, that n minus 3 is going to come down, and then I'm going to have to just like keep going and going and going, right? Like eventually like a fourth power will come down, and then a third power, and a second power, and a first power, and then I'll still have the c sub n there. Can you tell of any nicer way I might be able to rewrite that? This is awesome. Yeah, you probably spotted it. That's n factorial times a c sub n. All that factorial garbage that we were dealing with before, it was for a purpose. I didn't just waste your time. Okay, so now I can take a look at this and say, I know that when I plug 0 in for all the x's here, wait, there are no x's. Okay, so that just means I get this, and I want this to be equal to the nth derivative of f when I plug in 0. And I can turn that into a nice little formula that's f with nth derivative, plug in 0 over n factorial. This formula right here is awesome. It's so awesome. I'm going to box it up a couple times in a couple different colors. I'm going to put some added flair around it because it is this big of a deal. When I take a look at this, my mind should be blown because that's not just a formula for one coefficient. That's a formula for any coefficient. Take a look at all the red boxes. What would happen if I replaced n here with a 3? Then I would need how many derivatives? 3. And the factorial on the bottom would be 3 factorial. What's 3 factorial? It's 6. So if I plug 3 in, boom, I get the second to last box here. If I plug 2 in, I'm going to get this box. If I plug 1 in, I'm going to get the second box. And if I plug 0 in, I'm going to get that very first box we had up there. That's a really powerful idea. One thing that's important to note here is that when I do think about plugging in 0, I should keep in mind a quick note. Not n factorial. 0 factorial is defined to be equal to 1. That's a helpful thing to keep in mind. 0 factorial is not 0. It doesn't actually meet the original definition of what a factorial was, but we have reason to believe that 0 factorial could be equal to 1 or is equal to 1. It follows from the definition. If you're curious about why that is and like more information on it, by all means, just let me know, and I'd be happy to to explain that to you a little bit further. But this is a really powerful idea because this tells us right here how to get this polynomial. So before we end this video, I'm just going to write down one final definition here that kind of summarizes everything that we have. It'll say, if f can be differentiated n times at x equals 0. I might have to differentiate it a lot if I want to build some constants for it. Then we define the nth Maclaurin polynomial for f. This is the big name here that we're defining, an nth Maclaurin polynomial for that function to be, and we write it like this. we'd write a p of x, we just put a little subscript of an n on it right there. So that way we know that it actually is for telling us what the degree of that polynomial is. And again, if I use the formula that I have right there for the c sub n's, I can tell exactly what all the coefficients should be. You should be able to use that formula to confirm that c0 is f0. c1 is f prime of 0. And then on times an x. c2 would be f double prime of 0 over a 2 factorial, also known as just a 2. But I could be able to keep going here and say that c3 is going to look like this. And I could keep going on and on and on until I get all the way up to the nth derivative with a 0 over an n factorial x to the n. And now comes the real big kicker. This polynomial is built in to model the function f. And you'll notice it looks like a big, long addition problem. And this is where the ideas of chapter 5 will start to come back in. In the next video, we'll take a look at how we can actually use this in a couple different examples. And we'll have lots of examples as we move through the rest of the section to see kind of how these sorts of modeling polynomials actually work.